Hello students, welcome to the classroom point. In today's session, we shall discuss the questions on the states of matter. The first question is, calculate the weight of methane in a 9-liter cylinder at a 16 atmosphere and 27 degrees centigrade. R value is given. So, it is a question number 1 now. We know that the given data is temperature is given 27 degrees centigrade converted into the kelvins plus 273 equals to 300 kelvins. Pressure is given 16 atmospheres and volume is given 9 liters. Molecular weight of the methane is equals to 16 grams per mole. Now we need to calculate the weight, and R value is also given, that is 0.08 liter atmosphere per Kelvin per mole. So according to the ideal gas equation, PV is equals to nRT. Now PV is equals to N means number of moles, so it is weight divided by molecular weight into R into T. We need to calculate the weight. So weight equals to PV into molecular weight divided by R into T. Now let's try to substitute this given data. Pressure is 16 atmospheres into volume is 9 liters. Molecular weight is 16 grams per mole divided by R value 0.08 liter atmosphere per Kelvin per mole into temperature 300 kelvins. So by solving everything, we shall get the 96 grams. Option A is correct. Now let us solve the question number 2. What is the density of sulfur dioxide gas at STP? We know that density is equals to mass divided by volume. Here let us take the mass as the molar mass. Molar mass is nothing but the molecular weight. And here let us take the molar volume. So molar mass divided by molar volume. Molar mass in the sense molecular weight. Molecular weight of the sulfur dioxide is 64 grams per mole, whereas molar volume means 1 mole of any gas at STP occupies 22.4 liters of the volume. So that density is equals to, we shall take the mass divided by molar volume, that is 64 divided by 22.4. So we shall get the 2.86 grams per liter. So option A is correct. Let us solve the question number 3. What is the pressure of a mixture of 1 gram of dihydrogen and 1.4 grams of dinitrogen stored in a 5 liters vessel at 127 degrees centigrade? So first of all, according to the ideal gas equation, PV is equals to nRT. But we must note one thing, that here it is a mixture of the gas. So whenever the mixture of the gas is there, the pressure is called as the total pressure, volume is called as the total volume, number of moles are called as the total number of moles. R and T values remains constant. So we need to calculate the pressure, and before that let us try to put the number of moles of the given gas. So I'll write down the as it is for initially for one step. Total pressure into total volume equals to number of moles means sum of the number of moles of the both of these gases. Here hydrogen and nitrogen are there. So number of moles formula is weight by molecular weight. So weight of the hydrogen is 1 divided by molecular weight is 2 plus number of moles weight of the nitrogen is 1.4 divided by molecular weight is 28. They are the number of moles, and R value, always you remember that the volume is given in the liters. So pressure we will get in the atmosphere, so that R value you take as in 0.0821 liter atmosphere per Kelvin per mole into temperature is nothing but the 127 degrees centigrade plus 273, means we need to convert into the kelvins. This is equals to 400. Now the total pressure is equals to, we just take these values, 1/2 plus 1.4 divided by 28 into 0.0821 into, this is equals to 400 divided by volume comes this side, that volume is, total volume is 5 liters. So by solving this, we shall get the 3.61 atmospheres. Now let us see the answer that is placed on the other side. This is equals to 3.61 atmospheres. So here option B is correct. Now let us solve the question number 4. Let us solve the question number 4. In this question, 0.333 grams of alcohol displaced 171 cubic centimeters of air measured over water at 15 degrees centigrade in a Victor Meyer apparatus. The barometric pressure was 773 torr. Calculate the molecular weight of alcohol. Aqueous tension is given. We must observe that the alcohol is collected over the surface of the water. So means, just to see, this is the water, and in the Victor Meyer apparatus, just we are sending the alcohol vapors. So these alcohol vapors will be coming over to the water surface. Water surface means it includes water molecules also, that means moisture, wet. So this moisture and alcohol together, they have come out, and the total pressure of this gaseous mixture is, they said, 773 torr. Okay, so 773 torr is there. In this aqueous tension, separately they mentioned as the 13 torr. Aqueous tension is nothing but the partial pressure of the pure moisture, that is water vapor, that is 13 torr. Then we will get the dry vapor pressure. So pressure of dry air, that means alcohol, is equals to 773 torr minus 13 torr, that equals to 760 torr. This is equals to 1 atmospheric pressure. Okay. Now they are asking about to calculate the molecular mass of the alcohol. Okay, according to the again ideal gas equation, PV is equals to nRT. Now PV equals to N means weight of the alcohol divided by molecular weight of the alcohol into R into T. So we need to calculate the molecular weight. This has to be calculated. So that molecular weight is equals to weight of the alcohol into R into T divided by pressure into volume. So here weight of the alcohol, here they mentioned that is 0.333 grams. R value they did not give, but we have to take the liter atmospheres, that is 0.0821 liter atmospheres into temperature. It is at the 15 degrees centigrade. So 15 degrees centigrade means 15 plus 273, that is equals to 288 kelvins of the temperature, and pressure is equals to 1 atmosphere. Since we are taking the pressure in atmosphere, so that we consider the R value in 0.0821 liter atmospheres, and the volume they had given in the milliliters, that means cubic centimeters. Here R value is in the liter atmosphere. So you just see here R value equals to 0.0821 liter atmosphere per Kelvin per mole. That means volume must be in the liters, pressure must be in the atmospheres, temperature must be in the kelvins. In such case only this R value is applicable and valid. So volume is 171 cubic centimeters. 1 cc is equals to 10 power minus 3 liters. So we can write the 171 into 10 power minus 3 liters. So by solving everything, the molecular weight of this alcohol we get as 46 grams per mole. So it is equals to option C is right. Let us solve the question number 5. So in this question number 5, atmospheric air contains 20% of oxygen and 80% of nitrogen by volume and exerts a pressure of 760 millimeters of the pressure. So, this is the total pressure. Calculate the partial pressure of each gas. Means there is a container in which both oxygen as well as nitrogen is there. Oxygen comprises of 20% of the volume, whereas nitrogen comprises of 80% of the volume. Okay. So, when both of these together, their pressure, they are exerting the pressure of how much? The total pressure of this mixture of the gases is equals to 760 millimeters of the pressure. Now, they are asking what is the partial pressure of oxygen and nitrogen. Means individually their pressures they are asking. So, formula is partial pressure. I am writing the PP. Partial pressure is equals to volume fraction, just like mole fraction, into total pressure. Here volume fraction percentage is given, so this percentage we have to convert into the fraction. So, volume fraction of oxygen O2 is equals to given percentage value divided by 100. So, that we will get the complete fraction, that is 0.2. Similarly, volume fraction of nitrogen, we will get the 80 by 100 is equals to 0.8. So, partial pressure of oxygen is equals to volume fraction of oxygen, that is 0.2 into total pressure is 760 millimeters of the pressure. So, by multiplying this value, we will get the 152 millimeters of the pressure, and the partial pressure of nitrogen is equals to 0.8 into 760 millimeters of pressure. So, you will get the remaining pressure, that is 608 millimeters of the pressure. So, option A is correct. Let us solve the question number 6. The given question is 2.8 grams of nitrogen, 2.8 grams of carbon monoxide, 4.4 grams of carbon dioxide are found to exert a pressure of 700 torr. Find partial pressure of nitrogen gas in the mixture. First of all, I will write the formula for the finding of the partial pressure. Partial pressure of nitrogen is equals to mole fraction of nitrogen into total pressure. So, mole fraction of nitrogen, how to calculate the mole fraction of nitrogen? It means number of moles of the nitrogen divided by total number of moles of all these compounds. Which compounds are present? Number of moles of nitrogen plus number of moles of carbon monoxide plus number of moles of the carbon dioxide. So, individually, initially we have to calculate the number of moles. So, number of moles of nitrogen is equals to weight of nitrogen by molecular mass. So, given weight of the nitrogen is 2.8 grams and its molecular mass is 28, so it is equals to 0.1 mole. Similarly, number of moles of carbon monoxide equals to given mass by molecular mass. Given mass of carbon dioxide is 2.8 grams and molecular mass again 28, that is equals to 0.1. Number of moles of carbon dioxide is equals to given mass is 4.4 grams and its molecular mass is 44, that is equals to 0.1. So, mole fraction of nitrogen is equals to number of moles of nitrogen is 0.1 divided by total value of this one. So, it is equals to sum of these values, that is 0.3. We can write this value as 1/3. So, now partial pressure of nitrogen is equals to 1/3 of total pressure. Total pressure is given as 700 torr. So, 1/3 of 700 torr means we will get the 233.3 torr. So, option B is correct. Question number 7. Calculate the relative rates of diffusion of uranium hexafluoride, that is 235 uranium mass is given, and uranium 238 hexafluoride in the gaseous state. Atomic mass of fluorine is also given, that is 19. So, we know that rate of diffusion of any gas is inversely proportional to the square root of its molecular mass. So, if you take the rate of diffusion of the uranium hexafluoride 235, it is inversely proportional to the square root of molecular mass of the uranium hexafluoride 235. So I'll take this uranium hexafluoride 235 as the gas number 1, and the next one uranium hexafluoride 238 as the gas number 2. So here first of all let us find out the molecular mass of both of these compounds. So molecular weight of uranium hexafluoride 235 is equals to, uranium mass is given, that is 235 plus 6 fluorine atoms are there. So 6 into each fluorine atomic mass is 19. So total value is equals to 349. Similarly, molecular mass of the uranium hexafluoride 238 is equals to, here 238 plus 6 into 19, that equals to 352. So now let's try to see rate of diffusion of the first gas divided by rate of diffusion of the second gas is equals to the molecular mass of the second gas divided by the molecular mass of the first gas. Because if you take reverse R1 and M1, and R1 by R2 means M2 value comes to the numerator after the cancellation of the constants. So just you substitute the M2 value means second gas value, that is root over 352 divided by 349. So this value is approximately equals to 1.0043. So now R1 is to R2 values are is equals to 1.0043 is to, this is 1.000, whatever it may be. So option A is correct. Let us solve the question number 8. The given question is, the densities of methane and oxygen are in the ratio of 1:2. Calculate the ratio of rates of diffusion of oxygen and methane. So oxygen has to be taken in the first. And there is one more formula regarding the rate of diffusion. Rate of diffusion of any gas is inversely proportional to the square root of its density. So if you want to take the rate of diffusion of oxygen divided by rate of diffusion of the methane, that is equals to under root of density of the methane gas divided by density of the oxygen gas. So here density is already given. So density of the methane is given as 1 divided by, and oxygen is given as the 2. So this value, to solve this value is equals to 1:1.414. So 1:1.414 means option B is correct. Let us solve the question number 9. Calculate the molecular weight of a gas which diffuses through a porous plug at 1/6 of the speed of the hydrogen under the same conditions. So let's write down the formula for this. Rate of diffusion of the hydrogen divided by rate of diffusion of the gas is equals to under root of molecular mass of the gas divided by molecular mass of the hydrogen. And rate of the diffusion of the hydrogen, let us take it as a 1. So rate of the diffusion of the next gas is 1/6 of the hydrogen. So it is equals to 1/6. Root over molecular mass of the gas we don't know, which is need to be calculated, and molecular mass of the hydrogen is equals to 2. So molecular mass of the gas is equals to 72 grams per mole. Option C is correct. Let us solve the question number 10. The vapor density of a gas capital A is thrice that of the gas capital B. If the molecular weight of capital B is capital M, then calculate the molecular weight of capital A. So first of all, we need to write down the one formula, that is molecular weight is equals to 2 into vapor density. So whenever vapor density is given, we can calculate the molecular mass, means that they are directly proportional, because here 2 is the constant. So that we can write this form as molecular mass of A divided by molecular mass of the B is equals to vapor density of capital A divided by the vapor density of capital B gas. And they said that vapor density of A is 3 times to the vapor density of the B. So, and molecular mass of the B, they said capital M. So molecular mass of A divided by this value is capital M, that equals to vapor density of A is 3 times to the vapor density of the B means 3 by 1. So that now molecular mass of A is equals to 3 times the molecular mass of the B. So 3m. So option B is correct. Let us solve the question number 11. 3 moles of a gas are present in a vessel at a temperature of 27 degrees centigrade. Calculate the value of gas constant capital R in terms of kinetic energy of the molecules of the gas. So we need to calculate the capital R value, and a given data is temperature is given, that is 27 degrees centigrade converted into the kelvins by adding 273. So this is equals to 300 of kelvins of the temperature, and number of moles of the gas they had given the 3. So we know that kinetic energy formula is equals to 3 by 2 nRT. We need to calculate the R value. So R value is equals to 2 Ke divided by 3 NT. So R value is equals to 2 into Ke value not mentioned divided by 3 into number of moles, 3 into temperature 300 kelvins. So R value, just by solving everything, we shall get the value as 7.4 into 10 power minus 4 kinetic energy per degree Kelvin. So this is the answer. So option A is correct. Let us solve the question number 12. Calculate the average kinetic energy in joules of the molecules in 8 grams of methane at 27 degrees centigrade. So average kinetic energy form again is equals to 3 by 2 nRT. I shall substitute the given data over here, that is 3 by 2 into number of moles. Just will take the given mass by molecular mass, that is 8 by 16 into 8.314 joules per Kelvin per mole, and temperature is 300 degrees centigrade as the temperature is given in the kelvins. So kinetic energy now becomes 1869.75 joules. So option B is correct. Let's solve the question number 13. A gas occupies a volume of 2.4 liters at a pressure of 740 millimeters of mercury, keeping the temperature constant. Calculate its volume at standard pressure. Standard pressure they said. So here pressure is given 740 millimeters. So standard pressure here you take in the millimeters, that is 760 millimeters of the pressure. So initial, let us write down the given data. Initial volume is equals to 2.4 liters and initial pressure is equals to 740 millimeters of mercury. Final volume is to be calculated and final pressure is equals to 760 millimeters of the pressure, as they said standard pressure. So since the complete process is being taking place at the constant temperature, so we need to apply the Boyle's law. So according to the Boyle's law, P1 V1 is equals to P2 V2. We need to calculate the V2. So it is equals to P1 V1 divided by P2. So that it will be equals to 740 into 2.4 divided by 760. This is equals to 2.34 liters. So option B is correct. Dear students, hope you like the explanation. If you like it, please do share and comment and subscribe the classroom point. Thank you.